Hello, everyone. My name is Sean Bearden. I'm part of the Max Deventure Group at UC San Diego, and today I'll be describing a paper of mine, Critical Branching Processes in Digital Mem Computing Machines. Just a little background, this is a talk I intended to give at the APS March meeting, but the meeting was canceled due to COVID-19, aka the coronavirus. So I don't want to let these slides go to waste, so I'm going to put them online. Okay, so let's just do a little overview. I want to make sure that you're familiar with Mem Computing before we go in to discuss the fundamental units of Mem Computing, the self-organizing logic gates, and then we'll construct a circuit from those gates. Finally, we'll analyze the self-organizing logic circuit for avalanches and critical branching behavior. Then I want to wrap up with some new capabilities of our digital Mem Computing machines, which I'll describe more at the end. So first, Mem Computing. It is an efficient computing paradigm that uses memory to process and store information in the same physical location. Okay, it is not the same as in-memory computing. Okay, it's distinct from that if you've ever heard of it. It is a novel physics-based approach to computation. We leverage memory to compute efficiently, and additionally, time non-locality promotes spatial non-locality. That is, memory promotes collective behavior. Okay, so let's first understand the von Neumann architecture, right? The traditional architecture where the CPU and the memory are in separate physical locations. This causes what is known as the von Neumann bottleneck because information has to be passed back and forth between these two physical locations, causing a slowdown in computation. Now, in Mem Computing, we bypass the bottleneck by computing with and in memory. Okay, very important, with and in memory. But we want to stress that these Mem Computing machines are digital devices. They have input and output that could be read with finite precision. We don't actually build these devices, we simulate them. They're scalable in terms of resources. They're nonlinear dynamical systems with memory, robust against noise and structural disorder. They're capable of navigating non-convex landscapes via collective dynamics, and were designed to solve combinatorial optimization problems. But before we go look at a Mem Computing machine, let's first understand the fundamental components of the machine. Now you see up at the top right, we have this colorful pinwheel, but that's actually a circuit. And on the boundary are logic gates. So let's zoom in on one of these logic gates. Now this is just the representation is just a normal OR gate, but we have this double arrow in the middle to differentiate it from a regular OR gate because this is a self-organizing OR gate. All right, it is capable of changing its logic on its terminals to be consistent with the truth table associated with it. All right. There's also two NOT gates seen on the what would be traditional input terminals here, but we're going to ignore them in the truth table. All right. But this is a gate that can be ran in reverse. It's terminal agnostic. Signal can come in from any terminal. It can leave from any terminal. Very important to understand. But let's not look at this truth table. Let's try to visualize it a little bit more intuitively. All right. So there's 8 possible configurations for this gate, or 8 configurations that are consistent with the logic for this gate, right? But what we're going to do here is actually remove one of them by holding this output node fixed to true. All right, that's the constraint of the problem. We're going to use this circuit to solve a constraint satisfaction problem that I'll discuss in the next slide. So as you can see here, we have 7 other configurations that can be consistent with holding the output node to true, but that seems kind of easy to do. You have to appreciate the difficulty of the problem by looking at a very small example. So here we have a full circuit. It is very small, but you can see that the complexity of the connections blows up on you almost immediately. So there's only 10 Boolean variables in the original constraint satisfaction problem. We're looking at Boolean satisfiability problems here. All right, and those 10 Boolean variables get mapped into 10 continuous voltages, which are the color nodes that you see at the center of the circle circuit. All right, and then we have 43 constraints in the original problem that get mapped into 43 OR gates, And then the constraint is enforced by holding the output node of the OR gate to true. And then we let the system evolve, and it will solve the constraint satisfaction problem. So again, we don't actually build these, right? We want to analyze them. And what we can do, going to the next slide, is understand it from a dynamical system implementation. All right, so this is a dynamical system solving a constraint satisfaction problem. We can see it represented at the top left as a nonlinear ordinary differential equation of voltages and memory variables. The digital Mem computing machine is a topological computing paradigm that is robust against noise and structural disorder, and that's what we're seeing described at right. So let me get my laser pointer out here. So first, the system starts in an arbitrary initial state, and it falls into the nearest critical point. All right, now if you're unfamiliar with critical points, critical point just means that the system derivative is 0. Okay, so the initial state falls into the nearest critical point, and we see these black and red lines represented here. So the black lines represent stable directions, and the red lines represent the unstable directions. Now, what the system will do once it falls into a critical point is it'll jump to a new critical point via instantaneous trajectory, and that new critical point will be less unstable. Okay, so it's going to constantly jump, the system will constantly jump between these critical points, but the critical points will become more and more stable as we approach the solution, which we see down at the bottom. Now, these instantons represented here, right, these could be understood also as avalanches in the system. So collective flipping of voltages results in collective dynamics in the system, and the system jumps from critical point to critical point very quickly, falling into the solution. Okay, so we want to understand this avalanche behavior better, right? And we also want to understand why it helps us find the solution. What is actually going on here? So we did a little bit of near field analysis, and it implied the existence of a critical branching process and predicts a power law distribution of the avalanche size. So before we go into that distribution, let's first talk about the avalanches. How do we actually detect them? What you see here at the top of the panel are the voltages of a Boolean satisfiability problem with 420 voltages present, or they were Boolean variables turned into voltages. And you can see very easily that there's regions of inactivity where you see more white space, and there's regions of activity which have been boxed in blue. Now, those regions of activity are those avalanches that we're talking about. That's the jumping between the critical points. So visually, we can see them right there. It's very easy to detect but with the naked eye, but we need some method to do this where we can look at many systems and many solution attempts and get some statistics from it, right? So at the bottom, the way that the method we came up with to determine these avalanches is we first look at the magnitude of the derivative of the voltages in the system, okay? And we have to establish a threshold for this, which you can read about in the paper, but once that horizontal red line that you see, once you go above that red line, that's when we consider an avalanche to start. And then when the blue line dips below that red line again, let me get my laser pointer out. So if it dips above here and then dips below there, then that is the start and the finish of an avalanche. Now, for the whole time in between, we have to count all of the voltages that flipped. So counting all of those voltages, that's what we consider the avalanche size, okay? Now we go through, we collect all of these avalanche sizes for multiple variable size problems and multiple attempts at solving different instances of problems, and we result with what we see here. we find the critical branching behavior that was predicted by our mean field analysis. The mean field analysis predicted that the avalanche size would have a distribution, power law distribution with an exponent of -3/2. That negative s to the -3/2 is represented here. Just for comparison, this red line that you see, that's very straight. And then our data that we collected is shown above it. You can see just by visual comparison that it's very close, and the calculated exponent that we find is almost exactly -3/2. So great, very, very interesting, exactly what we were hoping to find. But the question may be, what do we do with it, right? What does this actually help us do? Well, we have these very large avalanches occurring in the system. Avalanches that can expand the entire size of the system, right? No matter how large the system is. So this is the type of behavior you want when you want to efficiently solve certain styles of problems. So can we leverage it? Yes, we can. We use these instances taken from the SAT competition, which you can go look at the website at the bottom. They are different ratios here. So the ratio is the number of constraints to the number of variables. All right, and what we find here is that there's 285 instances that are considered small-sized instances, and we can solve them all under the 5-second timeout established by the competition. Okay, now I said small size problems because that's what they're classified as, but that does not mean easy. It's very important to stress that. In the 2017 competition, the winner of that competition left 71 of these unsolved, and we solved them all. Now in 2018, that winner solved them all, but that's a different story. Okay, so this is very, very promising. We're solving these benchmarks that are being used in competition by state-of-the-art solvers that many of these solvers can't handle, and we're doing it well within the time frame of the competition. And I should also add, we use MATLAB. I'm not optimizing code in C++. I mean, I have an optimized version of MATLAB, but still, this could be improved in terms of the CPU time. So very, very interesting results, and we're very excited to move forward. I should also stress here too that the amount of memory that we use, since these are memory dynamics, is very small. For each instance seen here, there was less than 1 GB of RAM used during the solution search. Okay, so let me just wrap up here. This would be the portion where I would take questions. So if you have questions, you're free to email them to me. Again, my name is Sean Bearden. You can contact me at sbearden@ucsd.edu. And I would like to thank my funding sources up here, Alfred P. Sloan, DARPA, CMRR at UC San Diego, and the National Science Foundation. And again, I'd like to thank my co-authors, Max DeVentra and Forrest Sheldon. Thank you very much.